Okay, on to part 2 of volume entropy rigidity for convex real projective manifolds. So as a brief refresher, I'm going to let omega mod gamma denote a convex real projective structure on a manifold M, right? So this is omega is a properly convex domain in real projective space, which we represent by taking a slice of and pasting on our page here like this, and then we can understand, right? We can understand this as some tiling, right? Gamma acts on some fundamental domain, and you get some tiling, right? Where this is a hypothetical fundamental domain here. So I suppose in this case, M is an orbifold and gamma is a triangle group. And of course, the theorems that I'm about to state actually don't even apply for a two-dimensional example like this, but it's hard to draw tilings by three manifolds. So this is just a refresher. Okay. So the motivating question I left us off with was what characterizes the unique hyperbolic example in the space of convex real projective structures on M. And one existing answer is what's called the volume growth entropy. So this is the limb sup as t goes to infinity of 1 over t times the log of the Hilbert volume of a ball centered at any point x, it doesn't depend on the point, of radius t. Crampon in the compact case and Barthélemy, Marquis, Zimmer in the finite volume case proved that this quantity is bounded above by the dimension -1 with equality only in the situation where omega is the ellipsoid. Now this quantity here, or this inequality here, is proved in generality by Tolosane. In the finite volume case, Barthélemy, Marquis, and Zimmer are responsible for the equality part. Right? So the only way that this equality is realized is at the hyperbolic example, the constant curvature -1 example of the ellipsoid. Okay, so so here's another answer to this question of what characterizes the hyperbolic example. So this is proved in the compact case with Adeboye and Constantine, generalized to finite volume with Constantine. So we have a convex real projective structure on M. The dimension is at least 3, and M admits a hyperbolic metric. So that means that there is, M as a topological manifold can be realized as a quotient of the ellipsoid by a group of projective transformations. So under these assumptions, there exists a function of omega, which is uniformly bounded so that this quantity, the entropy raised to the dimension times the Hilbert volume, is bounded below by this value times n-1 to the dimension -1 to the dimension times the volume in the hyperbolic model of that same quotient. So this inequality holds, and equality can only happen in the case where omega is an ellipsoid. Now this is what I mean by a volume entropy theorem. So this is the volume entropy part of the talk is referring to a theorem like this. As one final remark, the entropy, the volume growth entropy, so this guy from before, the entropy of the ellipsoid is exactly equal to n minus 1. So another way of writing this expression here would be to replace that n minus 1 with the entropy of the ellipsoid. And so you'd see what's called the volume entropy functional on the left and the right here for omega and then for the ellipsoid. Okay. A little more about that, right? So this entropy functional, this is a linear functional in the metric. So if we rescaled the metric, this guy would also would remain constant. Oh, sorry, I'm saying a bunch of weird stuff. This is invariant under scaling. So this metric, if we rescaled it, right, if we had changed that factor of 1/2 in front of the metric to something else, then this would remain constant. A way to see that is, I gave you this definition of the entropy of omega, of the Hilbert metric, and there's another definition here, which is in terms of the lengths of closed curves. So as you rescale, that's a reason to maybe believe, right? This is lengths. So as you rescale the metric, lengths rescale. And then if you raise that to the n, it scales to the n. Or it scales to, so as you scale the metric, this will, like by k, this will decrease by 1/k, a factor of 1/k, and then this becomes 1/k to the n when you raise it to the n, and then you also scale that metric, so you change the volume by k to the n, and so the 1/k to the n with the k to the n cancels. So this guy is invariant under scaling, so this entropy functional thing. The reason I'll talk about in a sec some reason to care about that. Maybe here's a reason to care about this entropy functional inequality at all. Like, why would we care about such an entropy functional inequality? So one application is going to be a uniform lower bound on the Hilbert volume of our manifold. So we have this big space of possible convex real projective structures on M, and all of them have a volume bounded below by K. If we just rearrange this inequality here, right, we divide both sides by the entropy to the n, then we've seen before the inequality of crampon in the compact case and Tolizan in total generality, the entropy of omega is bounded above by n minus 1. So this is bounded below by 1. And there's only one hyperbolic metric on a manifold of dimension at least 3, which is a finite volume. So this is just some number. And so we have a uniform lower bound here. Because right in the statement of the theorem, we got that this function and omega is uniformly bounded. And so we get a uniform bound. So that's one application of a theorem like this. Another application, if ever, right, so same rearrangement from before written down. And if ever we had a one parameter family where the entropy of that family decreased to 0 with T, then the volume would have to blow up, right? All of these things, this thing is bounded. And so this guy goes to 0, so all of this blows up. So the volume of the Hilbert volume of these guys is going to go to infinity. Now this was proved already for certain examples. So there's a family of examples coming from Coxeter group study by Ni and Shang proved this in generality for surfaces, that this sort of thing that this can happen. And for those examples, the volume blowing up also did happen simultaneously. This is a result that says that generally, if ever the entropy goes to 0, the volume will have to inevitably blow up. So this can happen, that the entropy goes to 0, but that can't happen in the finite volume case. In finite volume, the Hilbert entropy is always bounded below by 1/2. And I'll cite Crampon and Marquis for that. Okay, so two applications of a theorem like this, two reasons to be interested in a theorem like this. So this theorem comes from, or the origin story for a result like this is the Besson-Courtois-Gallo theorem. If you're wondering, like, why would anyone ever care to prove something like this? This is the original theorem about these entropy functionals, the original volume entropy theorem. This was proved in the setting of negatively curved Riemannian N manifolds, compact, dimension at least 3 again. So if you have two such manifolds, oh, I already wrote compact there, so I didn't need to do it again. So they're compact without boundary. Assume the curvature of one of them, so assume the curvature of y is constant negative, then this entropy functional for x is bounded below by the entropy functional for y, and equality implies that they're homothetic. So this entropy functional is invariant under scaling, so it will never separate any two metrics that have just simply been rescaled, but up to homothety, this picks everything out. So another way of saying this is the hyperbolic, right? The constant negative curvature example minimizes the entropy functional in the setting of negatively curved Riemannian N manifolds. Now in our setting, we're looking at Hilbert metrics, which are not Riemannian. And we'll see that our result closely mirrors this one with this sort of cushion factor that pops out, that this inevitable cushion factor. Whether or not it's necessary is still an interesting question, which is not easily addressed with the methods that we've used at this point. Okay. So, and as a remark, theorems like this maybe don't look that interesting to you at first glance, but they have surprising consequences. Like, for instance, a corollary of this result is Mosta rigidity. If you have two hyperbolic metrics, then they'll satisfy this equality. Maybe something that you might want to confirm for yourself there. Two hyperbolic metrics will satisfy this equality, and therefore they're homothetic to each other. So if they both had curvature -1, then they would in fact have to be the same metric. And as a last remark, this is inspired by the Kataka entropy rigidity theorem for surfaces. So if you find this sort of fun and exciting, you should go read about that result. So this was trying to say something like that for dimension at least 3, or instead of just for surfaces. Okay, so the approach to proving these BC type theorems is the Besson-Courtois-Gallo natural map. So this is a map from, we wanted to go from quotient to quotient. So from our Hilbert geometry to the hyperbolic example. We'll start by building it on the universal covers, which are, okay, so obviously they're not going to be surfaces. It's going to be in 3 dimensions. We're not drawing a picture of that though. They'll go from omega to the ellipsoid. So we start with this point X, and we'll associate, right, so we could just send X over via a gamma a group equivariant map, which comes from the existence of quotients, right? So there's a homeomorphism between the universal covers induced by the existence of quotients. Okay, but right, because the quotient is the same manifold. That's just a homeomorphism. And what we want to do is compute derivatives. So we want to compute a Jacobian and to get to the volume control. So that's not going to be able to happen with this mere homeomorphism. So what we're going to do is smooth it out. So we take this point X and we associate to it a boundary measure. So mu X, which is a measure on the topological boundary of omega. And this will be a gamma equivariant measure. So for each x, there's a measure called Patterson-Sullivan measure on the boundary, which has a nice relationship to the group. For time, I don't think I'll be able to really talk about what it is. I'm just sort of giving you a flavor for what this approach is. But right, just to at least define for you what the natural map is. But there's a lot of surprising things that go into proving this theorem. Okay, so we've got this measure, which is a probability or a finite measure on the boundary of omega, and we associate x to that measure. And so we can just, now we do have f tilde, and we can just go ahead and push that measure forward to a measure on the boundary of, we can push that measure forward to the boundary of the ellipsoid here. Okay, we can just do that. And now what we'll do to smooth things out here is we'll take the barycenter of this measure. So we'll take a center of mass. So we'll take a center of mass of this pushed forward measure. Obviously the boundary is infinitely far away here. So with respect to the natural metric, there's a way to do this to make sense of this barycenter here. I'm happy to talk about it if you have questions in office hours, but I won't get too technical here. So essentially there is a center of mass associated to some measure on the boundary of the ellipsoid. And remember, the ellipsoid here is hyperbolic space. So hopefully that's believable to you, like that we could do something like that. Much more is possible when you're actually in the hyperbolic world, like constant negative curvature world here. So do all of this and you get what's called phi tilde, the natural map, which we will then project down. It will be equivariant every step of the way, right? F tilde is equivariant, the measures are equivariant, the barycenter will be equivariant because isometries. And so this will be an equivariant measure. So we'll be able to push this down to the quotients. And then the name of the game is to control the Jacobian of phi. So that's, I'm not going to talk about all this. That's a local argument. You take coordinates, you do a whole bunch of linear algebra. There's not much that I can say in the time that I have as to how this goes. It's quite technical. It's best to maybe, if you're interested, sit down with the paper and take a look. But the adaptation that we have to make to our setting, where we don't have the Riemannian situation, right? You're doing a local argument with linear algebra, and we don't have an inner product, because the Hilbert metric that we're looking at is Finsler. It doesn't necessarily come from an inner product. It has a norm, but it doesn't come from an inner product. So the idea is to adapt Bohlen-Neuberger's generalization of BCG to C2 Finsler metrics. And in doing so, this is where the n omega comes. They have an n omega as well. They have their own version of that. We can't do that verbatim. We have to have our own sort of trick for this, because the Hilbert metric is C1 plus alpha for some alpha which is bigger than 0. And in particular, if alpha is ever 1, so if we ever get to C2, then of course you're the ellipse anyway. So we'll never have anything C2 unless we're already the ellipsoid, which ends up being useful for the rigidity statement at the end. But in the meantime, we can't just approach with Bohlen-Neuberger's adaptation right away. So what we do instead is we compare the Hilbert metric to this so-called Blaschke metric. It's another metric that you associate to a properly convex set. It comes from affine spheres. I don't know much about that stuff. What we really use is that it compares acceptably well to the Hilbert metric. So this n omega that I mentioned before, here's the formula if you care. but it basically measures how far off is the Hilbert metric from being Riemannian, this Blaschke metric. So the Blaschke metric is a Riemannian metric, and this comparison here is going to measure how far off the Hilbert metric is from actually being that Riemannian metric. Maybe a few things to say about the Blaschke metric. So the Hilbert metric has the reason to look at the Hilbert metric is because it has those nice boundary measures associated to it. And those really hinge on negative curvature. So you have to have something that feels like a negative curvature to be able to build those boundary measures and then build this natural map. So negative curvature gives you these measures, and then you're off to the races. The Blaschke metric may be Riemannian, but you have no control over its curvature. It can be positive, it can be negative, it's all over the place. But at least it's Riemannian, and so we can get to a place where we're making some local arguments with linear algebra. I don't remember why I drew over these things, but I will say that these metrics might locally be very, very different, but they do compare uniformly. So there's a uniform constant that relates them, just because they're both projectively invariant. And this is an observation of Benoit Helene that uses a powerful theorem of Benzaprix. Okay, so that's why n omega that's sort of why n omega is bounded. You can imagine just playing with some inequalities here is all it takes to get a uniform upper and lower bound on n omega. And this guy is the Finsler metric that comes from the Hilbert metric, which is really what I should have written here. This should all be about norms. Anyway, okay, so that's all I wanted to say. Thank you for paying attention, and I have office hours Tuesday the 15th at 2 p.m. I think. So I hope to see you there or on Discord. Thanks.